Today's session, we're going to cover different types of processes that need to be considered during the analysis of segmental bridges specifically. We're going to go over those processes, and we're going to use MIDAS as reference program to be able to perform those processes. During the segmental bridge design, there are some things that we need to consider in today's webinar. The objectives are to learn about the functions for segmental bridge in MIDAS, temperature load application, as well as different types of loading such as centrifugal forces, braking forces. Also, we're going to perform a transverse analysis model, and we're also going to check serviceability as well as the tendon losses. As you know, for these type of bridges, those things are very important, and they have to be considered according to the different codes. We will start defining the process for application of centrifugal forces. As you know, this force needs to be considered when we have a curve type of bridge. In this webinar, we will cover a particular project application of a curve bridge, so we will consider this application during that time. The magnitude of the centrifugal force depends on the radius as well as the speed of the highway. Also the gravitational acceleration, as well as a portion of the load combinations. In order for you to define that particular load case in MIDAS, I will open up the program so that you'll be able to see it right away. How is that definition done? In this case, we have a segmental type of bridge. In this particular model, we've also considered the segmental construction, the segmental process for each segment, as well as the part of the substructure. And during this process, we will later on check how the construction affects the entire design of the bridge. In this particular model, we need, in order for us to define the centrifugal force, as I mentioned, this is a curved bridge. So in order for us to define that force, we have an option in MIDAS that allows us to do it using the equation that I just showed you on the screen, which is this one. In order for us to define it, the first thing that we need to consider is we need to define a static load case that has the centrifugal force. In order for us to define it, we need to use the load tab. And here we can define a static load case that is used for centrifugal forces. As you see in MIDAS, we have the different types of loads. So after we have that load case, we can go into element, beam loading. Here we can select the centrifugal force. According to the code, we can consider here the application. We first select the elements that we're going to apply the load to. And in this case, we're going to use a local axis of the element, which will be local y. And here we can define the magnitude of that load that we are going to apply for this particular load case, which is a centrifugal one. If we hit apply, we'll be able to see that load applied to the entire bridge, as you see here. This is one way of you that you are able to define the centrifugal force in MIDAS Civil. For these segmental types of bridge, I believe this is one of the easiest way to do it. Since it is a quick calculation, you can easily input that information in the program. The other type of load that we will also consider is the braking force. This braking force, as you know, should be taken as the greater of 25% of the axle weights of the design truck or design tandem, or 5% of the design truck plus the lane load, or 5% of the design tandem plus the lane load. According to AASHTO code, these forces should be assumed to act horizontally at a distance of 6 feet above the roadway surface in either longitudinal direction to cause extreme force effects. In order for us to consider that load application in MIDAS Civil, we will need to also define the braking force. As you see here, we already have it defined. So we basically can use the braking load case. And since the code requires us to define it 6 feet above the surface, we need to apply an eccentricity to it. An eccentricity can be defined using this eccentricity function. And in this case, we're going to use the offset as reference. We're using the offset because we are offsetting each one of the sections to the center top. If we go into the trim menu number 2, we can see the properties of each one of the sections. And here we are able to define or see what is the exact offset for each one of them, as you see here. So for each one of the segments, we have defined center top, and this is the reason why we use offset. And then from there, we measure the 6 feet the code requires. We define offset, and we use the global z-axis as reference to define that eccentricity. Here we assign the eccentricity, which is 6 feet. And then we select again the elements, and we assign a local x-axis, which will be the longitudinal axis for each one of the segments. Since the codes require us to apply the load longitudinally, we can use the local x as a reference. And here we can define the magnitude of the load that the braking force that we're going to apply, and basically click on apply. With this function, you're able to see the load applied at 6 feet from the surface, which is what the code basically requires us to do. This is one way of also considering the braking force on the entire bridge. Another thing that we will consider for this particular bridge is the temperature loading. As you know, temperature gradients are caused by top and bottom surface temperature changes. You know, the structure gets warmer at the surface, and then since we have big amounts of or masses of concrete, that temperature variation affects the behavior of the bridge. So that is the reason why we need to consider these temperature gradients. In MIDAS Civil, we have multiple ways of defining temperature loading, and we're going to focus on the temperature gradient itself. We have something called temperature loads. Basically, what you can do with this function is you can define a temperature gradient as you see here, or a variation on the entire section. You have two options, the gradient or the beam section temperature here. In case of temperature gradient, only the temperature differences between the top and the bottom can be defined, which is this part. In the case of beam section temperature, the temperature differences for certain locations on the section, you can enter them manually, depending on what the code requires. We also have a function called PSC for the temperature loading. Uh, in here, basically what the program does is it automatically defines the temperature load by dividing and transforming the corresponding zone, as you see here. So from the top portion of the segment, it will generate a transform portion of the section and basically apply the temperature changes there. In order for us to do that in MIDAS, we can use the temperature functions, which are here, and we can define a beam section temperature, as you can see here. And then from there, we can consider the PSC composite type of section. Here, we can define what is the difference in temperature, as well as the heights for each one of them, like the locations of where the temperature changes along each section. In order for us to define the temperature, we first select the temperature load. We select the elements that we're going to consider for that load application, and we're going to apply it at the top portion of the segment. So in this case, what we're going to do is we're going to basically define what our B is. B is like basically the width of the section, or the portion of the width of the section that we want to consider for the temperature loading. We also can specify the height, which will be the distance from the top portion of the segment, which is H1. Also, we can define H2, which is basically where we're going to, where exactly from, with respect to the top portion of the section, where is exactly the temperature location at the bottom portion. And we can also define what is the T1 and T2, which is the variation from the temperature from this T1 to this T2, which are related to H1 and H2. So here, B 30 feet, we're going to select H1 as 0. We're going to consider the surface as our initial position. Our H2 is going to be 4 inches from the top, and we are going to generate a temperature variation from 54 to 14 degrees Fahrenheit. We simply click Add and apply it on the entire surface. You can consider the units as Fahrenheit. If the program has other type of units, you can simply come into the Tools tab, Unit System, and here you can define which temperature unit you want to consider. After this, we're going to run the analysis for this particular bridge, and we can run the analysis using this button right here. After we run the analysis, we can define in the program, we can check which loadings are and which moment diagrams are being applied at each particular stage. Here the model is running. What we're going to do is we're going to check the moment diagrams as well as the forces that were generated during those due to those loads that we just applied. And as you know, in segmental bridge analysis, we also have to consider the forces that happen during construction. Those forces are tend to be the most critical ones because those are usually the highest forces, at least moments and shears that the segments are subjected to. Construction sequences involve traveler, formwork, as well as wet concrete, pre-stressing, construction loadings. Since all those things happen at the same time, we have to find a way to consider them all during the analysis of the bridge. Usually, we consider the most critical um, factors or situations right before putting the key segment, after closing the bridge with the key segments, and also long-term effects due to the creep shrinkage as well as the tendons. This is what we're going to consider right now, as well as we're going to check the forces that we just applied in the model. In order for us to do that, first thing I want to consider is for beam, if we right click after running the analysis, we can check forces as well as deformations and the different types of results. If we go into the results tab, we can check forces, beam diagrams, and here we can check the forces due to the centrifugal loads as well as the braking forces and their effect on the piers as well as the forces on the segments. We can also consider, for example, for centrifugal forces, we can consider the torsions that are generated on the segments, which is for due to the MX. And if we want to consider the legend, we can also apply that legend and see what effects are happening during this process. One thing that we also have to consider is that in MIDAS Civil, we can define the construction sequence, and that construction sequence can be checked one by one as we pour the different segments. For example, if you want to check the shear forces, which will be FC for when we pour the second segment, we can check what is the shear force that is being generated along the entire bridge. We can also check the pier forces, and we can also check the moment that is being generated and the effect of the construction on the entire bridge. As you know, MIDAS Civil also considers the formwork as well as the equipment loads as well as the traveler. And all those loadings are being considered with their moments as well. And we can check all those effects during the entire construction of the bridge, as you see here. We can see the short term. We can consider what is the effect due to the tendon primary forces as well as the tendon secondary forces. And here we can check what is the effect of each one of the tensionings for tables. In table format, right before closing, since this is one of the most critical situations that can happen, these situations needs to be considered in very detailed, as well as for a particular report. If you would like, for example, to consider the summation for all the forces at this particular stage, which is right before closing, there's an option in MIDAS in which you can generate a dynamic report for this, as well as the shear force. You can also create a dynamic image, as well as the axial forces, because here we are considering the tendons. You can generate an image, and then you can use that image in your particular report. One of the things that we need to consider is also after we close the bridge with the key segment, we need to see what forces are generated along the entire bridge. And there's another thing that we need to consider, which is after the 10,000 days, as the code requires. What happens due to the tendon primary and tendon secondary forces after 10,000 days? You can also consider that in the program, and you can also obtain your forces and moments along for those long-term effects as well. So we have 3 images that we saved, and we also were able to check the different forces as well as the different diagrams in each one of the, let's see, for the summation, short and long term for each one of the stages for construction. After you review the different forces, we are going to do a deflection check, serviceability, basically check. Serviceability can be checked in MIDAS Civil using the moving load analysis, as well as considering the impact loading and the life load. As you see, ASHTO requires us to check, depending on the location that we are looking on, in this case, a segmental bridge, the general deflection criteria is basically maximum deflection will be the span divided by 800. If it's vehicular load and pedestrian loads, the span divided by 1000, and is for the cantilever arms is a span by 300. In this case, we can easily check those deflections in post-construction stage. We can use the displacement contour option, and here we can select the impact plus the truck and check what is the deformation on this particular bridge. Here we can change the units here at the bottom if we want to consider inches, and here we can see what the deformation is. If we also want to consider only the vertical axis, we can check vertical axis and see what is the deflection of the bridge due to that life load plus the impact loading. This is something that needs to be checked just to make sure that we are under serviceability, and this is how it is done in the program. It's a very simple step. You can also save an image for this, and then you can use that image for your report. Last thing I want to consider before generating the portion of the report is the transverse section analysis. Transverse section analysis basically is an analysis that is required, and it basically is changing the position of the trucks along the transverse direction of the girders. In order for us to change or to be able to generate this type of analysis, you can either do it using spreadsheets, or in MIDAS Civil we have an option that automatically generates the transverse analysis section for you. This option is called Transverse Model, which is this one. And this Transverse Model, basically what it does is you can select the element that you want to consider for the transverse analysis. Let's say we want to consider element number 24 for this particular model. Or here, after you select the element 25, you get to tell the program which part of the element or position you want to use. I or J node, you add here, and the program will automatically create a transverse model from there. But before you do that, you need to define what is the location of the pavement, as well as the location of, let's change it to feet, the location of the barriers and so on. So in order for us to define that location, we first need to tell the program what is the distance for the barriers, as well as the distance for the median strip, and also the distance for the asphalt, which is this portion here, as well as this portion right here. E5. After that, we can define whether you want to use a support or a spring to support this transverse section. We can define the loading that we want to consider with the magnitudes. You can change this. And we can also define what is the live load distribution that we want to consider. We can tell the program the loading, the axis that we want to consider, as well as the number of axles that we want to consider. If you want to consider the wind load, the program also can generate the wind loading. And if you want to use tendon information or reinforcement, you can define that tendon information and reinforcement. After you do that, you define it. And after you define it, you can export it. When you export the section, you can simply open it. It's the J node for element 25. And here we are opening that particular transverse analysis model that the program automatically generated. Here you can see that program generates the self-weight, temperature gradient, temperature loading, as well as the collision loads, barrier load, as you see here, and also it defines the traffic lane with the vehicle. You can see the axis of the vehicle here as defined in the transverse model function. And after that, you just need to run the analysis, and from there you can create a transverse model easily. Here we can check the forces for the transverse analysis model. As you see here, we can also check this due to the self-weight. We can also check the forces due to the moving load. we also can check with the moving load tracer what is the location of the truck that generates the highest moment in this case, or the lowest moment. And from there you can specify in the program what is or do the entire modeling and analysis of the transfer section without having to use the spreadsheets or just using the MIDAS application. If you want to consider the legend, you can also consider the legend as you see here, and from there you can do the transverse analysis model. After you're done with the transverse analysis and with the modeling, you can generate a report of the sections and the different cuts that we have considered. In this case, we have something called Dynamic Report Generator, which is under the Tools tab. Here you can open a new document or you can open an existing one. If you have a template, you can open the template, or you can consider a new document, as you see here. And then from there, if you want to define the moment diagram, you can simply drag and drop it from the ones that we have previously saved. So here we can start typing. It's basically Microsoft Word inside of the program. This is the moment diagram before key segment. Here you can type forces review before key segment. And here you can start write the description of what you're going to display. This is pouring segment number 8 from the balance cantilever, and this is the most critical one because it's right before closing the bridge. So you can drag and drop moment diagram, shear force diagram, as well as the actual forces due to the tendons, and then serviceability check. Here we can define our serviceability parameters that we mentioned earlier, and we can bring that information into MIDAS Civil. Here we can define the serviceability, and from there you can bring the image into your report. That way you can easily create a report just by simply taking the parameters that we have considered for the superstructure, and you can create an entire report by you considering this information. There is something that also needs to be considered when you are doing the design of these type of bridges, and that thing is the stress diagrams that need to be checked. We have something called bridge girder diagram, and for this bridge girder diagram we can consider a particular load case or load combination that we want to use for the stress checking, and we can specify which portion, whether it's top or bottom portion of the segment, and what is the allowable stress with the lines that we can consider. In order for you to generate this report, you need to assign the entire superstructure or the segments into a group, and then from there simply click apply, and the program will display a diagram like this one with the allowable tension as well as the allowable compression that you define. This is very important because you can also use it in your report and to see or to show that you're not passing the allowable stresses in tension or in compression. As you know, these stresses depend on the strength of the concrete, but there is a range that the codes allowed us to use. So we might as well, with these lines, we can also draw those allowable stresses in tension and as well as compression, as you see here. With this information, then as the final output for segmental bridge design, in MIDAS Civil we have our code check. You can do code check as per CSA as well as AASHTO LRFD. And here you can check whether the segments are under the allowable limits specified by the code in terms of flexure, shear and torsion, stresses on the tendons, allowable stresses, as well as construction allowable stresses. So the first thing you need to do is define the code that you want to consider, and then define the parameters that you want the program to use for that code. Whether you want to use, the corrosion conditions, flexural strength, and the output that you want to consider, the material that you want to consider, as well as the material for the rebars. After that, the design position for output and design position. Design position is basically a check. Design position for output is a report that the program can generate. So you get to choose which elements you want to use for the report. Allowable stresses, this is basically the load combinations that you want to consider for each service limit state. And then from there, you can perform the design. And here, the program, what it's going to do is going to do a code check for each one of the elements that you pick for the design position. The code check will use parameters from AASHTO to generate a report, and also it will generate tables that will be or can be used as reference to check whether or not the segments are under the allowable or by the limits of the code. In this case, we're going to the program does the code checking in the background, and the program, as I mentioned, also has an option for generating a report, which is this Excel report function that you can see on the screen. This Excel report option basically generates a Excel report with the properties of the sections as well as the materials, the tendon information, and then it starts doing the code check, positive moment code check for a particular load combination. It also generate a neutral axis, and it will also check the forces on the tendons. It will do a flexural resistance check with the clauses of the code as well as the different equations that the program uses. Negative moment, and it will tell you whether or not it passes the code. Shear, calculate the shear capacity, and it will tell you if the sections can handle that shear resistance, as well as shear and torsion. Keep in mind that it's important that you notice that the program has all the equations that it uses, and that this is an Excel sheet that you can edit. So you're able to manipulate and use this information, and you can always print it and have it as your report. Tendon stresses are also checked for each one of the tendons, as you see here. Different principal stresses at construction stages as well are checked for this particular element that you select. So it's very important that you see how detailed this report is and how it can benefit you during your superstructure design and code checking. After you run the design check in the program, you can see the different stresses during the construction stages, as well as pre-stressing in the tendons, principal stresses during the construction stages, flexural strengths, and you can see whether or not you pass the code. If you don't pass the code, then you can go back and check the rebar information or increase the tendons, depending on what does not pass. Combined shear and torsion, you can also check, and you can see whether or not you need more rebar. There's also an option in the program to check the PSC result, and here you can see demand, capacity versus demand in terms of forces. So it gives you a pretty clear idea of where the problems are along the bridge. So with this information, you can go back and do your code checking. So with this, we finished this session with the superstructure analysis and check, and these specific loadings that we have defined along this webinar. Thank you very much.